If you've ever looked closely at a piece of honeycomb, you'll have noticed something striking. Every single cell is a perfect hexagon. 6 sides, 6 equal angles, repeated thousands of times across the comb without a single gap, without a single overlap. It looks less like something built by insects, and more like something drawn with a ruler and compass. Now here's the question that seems almost too simple to ask. Why hexagons? Bees are insects. They don't study geometry. They've never seen a textbook. So how does every colony of bees, on every continent, in every corner of the world, independently build the same mathematically perfect shape every single time? Most people assume it's just instinct. There's no deeper reason. But there is, a mathematical one. So precise that human mathematicians spent centuries trying to prove it on paper and didn't fully succeed until 1999. The bees had been getting it right for 30 million years before that. To understand why hexagons, you first have to understand the problem bees are actually solving. A honeycomb has one job: store as much honey and as many eggs as possible in the smallest space, using the least amount of wax. Wax is expensive, not in money, but in energy. A bee has to consume roughly 8 grams of honey just to produce 1 gram of wax. In a colony surviving an entire winter on stored food, every gram matters. Wasting wax on an inefficient structure could mean the difference between surviving the cold months and starving before spring. So the bees need a shape that tiles perfectly. No gaps, no overlaps, using the minimum possible wall length. And when you frame it that way, the question becomes a mathematical puzzle with one specific, provable answer. The most natural shape for a small container is a circle. And bees actually do start each cell as a rough circle. It's the most natural shape for a bee to form using its own body as a guide. But circles don't tile. No matter how carefully you arrange them, there are always gaps between them. Wasted space, wasted wax. So circles are ruled out immediately. There are exactly 3 shapes that tile a flat surface with no gaps at all: triangles, squares, and hexagons. That's it. Every other shape leaves holes. Triangles tile perfectly, but they have a lot of edge relative to the area they enclose. More edge means more wall. More wall means more wax. Squares are better, less edge, less wax, but still not the most efficient. A hexagon tiles perfectly and encloses more area per unit of wall length than any other tiling shape. For the same length of wall, a hexagon stores more than a triangle or a square. Build your comb in hexagons, and you store the maximum amount of honey using the minimum amount of wax. No other shape does this better. Here is the detail that makes this truly remarkable. This idea that the hexagon is the optimal tiling shape is known as the honeycomb conjecture. Mathematicians first proposed it formally in ancient Greece. For over 2,000 years, everyone agreed it was almost certainly true, but nobody could prove it. Not the ancient Greeks, not the mathematicians of the Renaissance, not the great minds of the 18th or 19th century. It wasn't until 1999 that a mathematician named Thomas Hales, using modern computing tools, finally produced the complete proof. The bees had been using the correct answer for 30 million years. It took human mathematics until 1999 to catch up. The next time you see a jar of honey on a shelf, consider what went into it. 30 million years of evolution landing on the same answer that stumped mathematicians for 2,000 years, not because the bees learned it, not because they planned it, but because nature, given enough time, always finds the right answer. If this gave you a new appreciation for something as ordinary as a jar of honey, give the video a like. Share it with someone who loves bees or maths, or both, and subscribe to Why Is That for more fascinating stories hiding in your everyday world. Thanks for watching,